And if you recall, in calorimetry, even with enthalpy, we did calculations where we might be trying to find out something about the system by what happens in the surroundings, or by what happens in the surroundings by what happened in the system. And a similar kind of thing is going to happen here with this entropy change. We're going to kind of change it around so that we have items that we can track that have to do with the system, and that's going to make our life easier. Excuse me. We're not going to have to try to measure some entropy change in the surroundings. All right, our last thermodynamic energy function, Gibbs free energy, is a state function. That only means, what that means is that it doesn't depend on where you are. It depends on where you came from and where you are right at the present time. It's a change, not just where you are right now. Now remember, I told you that most exothermic reactions can be termed as being thermodynamically favored, but not all are, okay? We talked about how we have, a lot of times in solution dissolving, we have endothermic reactions that are also thermodynamically favored. They happen. And let me just throw in right now, because this sometimes, if a reaction occurs, some of these things occur to me, and if it occurs, that means it is spontaneous, right? It's happening. This Gibbs free energy, you'll see that we can relate it to our delta H and our T delta S. We're going to talk about why we can do that in just a minute. And why that's important, the Gibbs free energy can tell us how much energy is available or free. This is why they call it the Gibbs free energy. It tells us how much energy is available or free to do useful work. Because that's really what we'd like to know, right? We'd really like to know how much work can we get out of this system, or how can we change this system so we can get more work out of it. What would we have to do? We talked about that a little bit when we talked about Le Chatelier's principle. We talked about we can increase reactants, we can take out products. Again, a chemist is trying to figure out whether something can, how much useful work can we get out of the system. All right, so in its most useful arrangement, our Gibbs free energy, our standard Gibbs free energy is equal to our standard enthalpy minus our temperature times the change in entropy. And so we see that it's not just the enthalpy, it's not just the entropy, but it's both that kind of decide how much free energy or energy we have left over to do useful work. And again, we've said that if enthalpy again, I've underlined tens because I've tried to highlight that there are endothermic reactions that do happen. They occur. You can take ammonium chloride, you can dissolve it in water. The flask gets cold, it's an endothermic reaction. It did dissolve though. So it must be thermodynamically favored. And so that's why exothermic reactions tend to be, and I should have said thermodynamically favored. All right, I'm running out of room. Thermodynamically favored. If we have a change in entropy that is positive, that tends to be thermodynamically favored. But we can't always tell. So the story that is true about Gibbs free energy is that we can't look just at whether a reaction is exothermic or endothermic. We can't look at whether it's just an increase or a decrease in entropy. It's kind of like a tug of war. Bless you. Since our exothermic being negative tends to be favored, and if our enthalpy was negative, and our positive tends to favor a thermodynamically favored, and then we minus it, when our standard free energy is less than 0, that is a spontaneous or thermodynamically favored reaction. Okay? If delta G is greater than 0, it means that at that temperature and pressure, it's non-spontaneous or not thermodynamically favored. Yes? What are the units? Well, we have to get our units. The units for delta H are kilojoules per mole. Our units for entropy are joules per Kelvin. And so I'm glad you brought this up. When we start to actually do problems, one of the things that you will need to be aware of and to be careful of is to always make sure these units are in sync with each other, right? And you'll notice that once we put our entropy in, our temperature, our Kelvin, is going to cancel. So then what do we usually have to do? We have to keep track of whether we have joules or whether we have kilojoules, right? Yes?
For entropy, that's joules over Kelvin, right?
Correct. That's joules over Kelvin. Any other questions? Okay. If it is greater than 0, it's non-spontaneous. Now, this non-spontaneous doesn't mean we can't get it to occur. It just means that at that temperature, it's non-spontaneous, right? Maybe if we raise the temperature or something like that. In 101, there's a chlorate reaction that at room temperature, it's just a pile of white ionic compound. And if you heat it up, the bonds break and the oxygen is released. And you don't even really need to know what the exact equation is, but by raising the temperature, we changed it from a non-spontaneous reaction to one that's thermodynamically favored. All right, if this equals 0, then we're at equilibrium. We are going to talk about that a little bit later, as you might imagine. The free energy state function is similar to our enthalpy. The delta G of